All right, so homework for Tuesday was the multi-threaded merge sort,
Yeah.
right? How'd that go?
Fine.
Okay, let's,
Me and Emily had a little debate about what was correct, and we didn't really come to a conclusion.
what was, well, I suppose you could have a couple of different versions of this that might be correct, but let's.
Was the idea to have like two threads, one does the first half and one does the other half, or was it to have one thread for each like split?
You're getting your most efficiency from one thread per each split,
Okay.
but I'm not sure it necessarily makes that big of a difference because you're really doing the same thing. I mean, you would have to only do you would have to do it as a special case to just do the first half and the second half and just have those threads do those simultaneously. You would have to say, only do this the first time. Let's see where we go with it.
Like I did it wrong then.
Does that surprise you?
No. This assignment was like probably the hardest one for me. Writing is weird. It does not fit well in my head.
Okay, so I have an example of our worker bee. So what I'm going to go ahead is we're going to, let's see, do we want to write this in a new, we want to do this in a new repository? Okay. Okie dokie. All right, so we're going to call this guy CSC250.
Hey, Littman.
What's up?
Can you share screen with us? Thank you.
There you go. All right, CSC250 merge sort threaded, multi-threaded. All that pretty good. And we're storing this in repos. Okay. And then we'll go back out here, move this, hide that. I'm going to create a new Java project. And we're going to name this guy CSC250 multi-threaded merge sort. We're going to put this in our repos directory. Inside of merge sort multi-threaded. And then don't create our module. Then I'll go ahead and give ourselves our driver class. All right, we have a running program. All right, so what we want to do is we want to create our merge sort, right? And the idea is our merge sort is going to be a multi-threaded merge sort. And we want to kind of plan this out, decide how this is going to ultimately work. This is 250. So we're going to draw some pictures. So we have our original data. And so we don't even need to put numbers in there. We'll just have our original data. And then what we want to have is we want to split this guy into two. All right. So we have, this is our main thread. As I mentioned last time that all programs start off in a single thread, the main thread of execution that we didn't create, it just exists. So when we decide, oh, this guy's not sorted, he's not a one list, I'm going to go ahead and split it into two, and I'm going to have a worker B thread, WBT, worker B thread, and another worker B thread handle each half. Now this guy will get split into two halves, worker B thread, worker B thread, so on and so forth. Okay, so the job of our worker B thread will be to do the splitting, spawn off threads, wait for those threads to finish, then do our merge. Make sense? Okay, so we're going to go ahead and create our worker bee. So we're going to call this guy a merge sort worker bee. And we'll have him extends the thread class. And remember, inside thread, we need to have a public void run function. So we'll just go ahead and create that. But we're also going to have a constructor for our merge sort worker B, and we'll fill that in here in a minute. Okay. So out here in driver, we want to go ahead and create a array of some random numbers. All right, how many numbers do we want? 20? Good enough. So we'll have int array AR is equal to new int array of size 20. Then we want to go ahead and fill that guy up with random numbers. So for int I is equal to 0, I is less than AR.length, I plus plus. And we want to say AR at bucket I is equal to, we need a random number. So I'm going to go ahead and give myself a random generator. Random R is equal to new random. And we'll import java.util.random. So now I can say r dot next int, and we'll give it to 1,000. So we'll do 0 to 1,000 just so our numbers look somewhat palatable instead of the negative 2 billion to positive 2 billion numbers. All right, I'll go ahead and write a quick function to print array. This guy will take in an int array as a parameter. And what I'm going to do is I'm going to say system.out.print AR at bucket I followed by a space. And then I'll say system.out.println, just the empty string. All right, so this will be a more compact way of looking at my data all on one, it'll probably do wrapping, but it'll be mostly on one line. It'll probably be 7 or 8 lines, something like that. So I'll go ahead and do driver.printArray AR, and we'll run this, and we should have our list of 20 numbers all on one line. Okay. So now we have our random numbers. So this is a single array that I want to call merge sort on. Okay. Who knows how to do merge sort? Well, we're going to teach our worker bees how to do merge sort. So when we build a worker bee, we're going to pass it the array along with the position, the portions of the array that they're in charge of working on. Make sense? So go into our worker bee, and this guy is going to keep track of a private int array AR, but keep track of a private int begin and a private int end. Okay, he's going to keep track of 3 pieces of information. This should look pretty similar to what we did when we originally called merge sort. We're just embedding merge sort inside of his own thread. So now the constructor for our merge sort worker B is going to take in an int array, an int begin and an int end. And we'll set this dot AR is equal to AR, this dot begin is equal to begin, this dot end is equal to end. Keep in mind that arrays are passed by reference, passed by address. So I'm giving this worker B a pointer to the actual array that lives in memory. And his job is to sort that guy with between begin and end. Make sense? Okay. Now, inside of run, I want to go ahead and I just want to give a little like feedback that, this worker bee is getting started, something like that. So I'm going to go ahead and say system.out.println, put a couple of asterisks. Then this dot, what is it? Get ID. Is starting. So this dot get ID, this will be the unique ID of this particular thread. It'll be some number that should be unique to him, at least telling us that we have a new thread. Let's say starting between begin and end. So it'll tell us what portion of the array it's working on as well. Okay. That way we'll just have a little visual feedback each time we spawn off a thread. Okay. So what run is going to do is he's going to ask the question, if begin is not equal to end. So really he's asking, is this the one list? If begin is not equal to end, then what do we want to do? We want to calculate the first half and the second half. So we'll say int begin 1 is equal to begin, int end 1 is equal to begin plus end divided by 2. Int begin 2 is equal to end 1 plus 1. Int end 2 is equal to end. So those are the beginning and endings of our two halves. Then what are we going to do? We're going to create some worker bees. So I'll create a merge sort worker bee. We'll call this guy left half. We'll pass him the array begin 1, end 1. Like this. We'll also create one for the right half. This will be begin 2, end 2. All right. Now, both of those guys, though, we need to wait on because then we need to merge. The merge step happens after this, correct? But we can't start the merge until the two threads above are done. So we have to wait for those threads. So after I spawn them, I'll say left half dot join, and I'll say right half dot join. Now these guys are inside of a, they throw an exception. So I'll do all this inside of a try catch. So I'll try to join left half and right half, waiting for these threads to do their job. Then I'm going to do my merge step here. Now, I can write merge right here, or I can write it inside of its own secondary function. I don't know. I don't know if one's better or worse than the other. Let's just write it in here. All right, so once this returns, we know that left half is sorted and right half is sorted. Both of those sides are sorted. So now I need to merge them together. Okay, so I'm going to have a int array called temp, and this guy's going to be equal to a new int array of size end minus begin plus 1. So that'll be the size of my new array that I need to copy stuff over to. So if I'm looking at bucket 0 through bucket 5, let's say, 5 minus 0 is 5 plus 1 is 6. I have a total of 6 buckets that I need to place. Okay, so temp is going to be that guy. Then I'll say int pos1 is equal to begin 1. Int pos2 is equal to begin 2. So I'll set those guys up at the beginning of my 2 halves. And I'll have my for loop. So for int I is equal to 0, I is less than temp.length, I plus plus. So we're going to go through and place temp.length number of values into temp based on who the winner was from our 2 lists. Okay, so we're going to say if pos1 is less than or equal to, well, let's say if it's less than begin 2, and pos2 is less than or equal to n2, that means they're both currently legal positions, right? And if we rather say less than or equal to n1, that works too. If you would say pos1 less than or equal to n1 and pos2 less than or equal to n2, they're synonyms for each other. So this basically says if pos1 and pos2 are both legal positions, then we'll ask if AR at bucket pos1 is less than AR at bucket pos2. If he's the winner, we'll set temp at bucket I equal to AR at bucket pos1. And then we'll say pos1 plus plus. Else, temp at bucket I is equal to AR at bucket pos2. Pos2 plus plus. So this is if pos1 and pos2 are both pointing to legal places on their portion of the list. Then we'll just ask if position pos1, the element at that position is less than the element at position pos2, then pos1's the winner, we'll place him in temp, increment pos1. Otherwise, pos2's the winner, we'll place him in temp, increment pos2. Else, if pos1 is less than or equal to n1, that means pos1 is our winner. Increment pos1. Else pos2 must be our winner. Increment pos2. And this will place temp.length number of things, which should in the end get pos1 and pos2 both to be legal positions. If they're both legal, pick the winner. If only one of them is legal, if pos1 is the legal one, he's declared the winner. If pos2 is the legal one, he's declared the winner. Okay. Then we need to copy the contents of temp back into AR from begin to end. from those two positions. Okay. So we need to go and get each element from temp. So we're going to say for int I, actually, let's go, let's see, let's call this temp pos is equal to 0. And then we're going to say int AR pos is equal to begin. I think it's actually like that. Then we'll say keep going as long as temp pos is less than temp.length. We know that's the number of times we need to go through. And then each time through, we'll say temp pos plus plus, and we'll say AR pos plus plus. So we can use a single for loop to give ourselves 2 counters. This is allowed. Otherwise, you could put a variable beforehand and just make it work. But I'm declaring a temp pos is 0 and an AR pos is begin, because I'm going to go through temp from bucket 0 to bucket temp.length minus 1. And I'm going to go through AR pos from bucket begin to bucket end minus 1. Does that make sense? All right. So Dr. Locklear was just dancing in the hallway. I don't know what he was doing. All right. So what we're going to go ahead and do is we're going to say AR at bucket AR pos is equal to temp at bucket temp pos. So we're just copying back over into AR at the correct positions the things we stored inside of temp, overwriting the stuff that's currently in AR because we've now sorted it through our merge step. And because AR is passed by address, because this guy is passed by address, we're changing it in real memory. Make sense? All right. So that is what we do. And then we'll do a catch down here. Catch, exception, E dot print stack trace. That'll print out our something went wrong with our threads error message thing in the event that joining it was a problem. Okay, so run inside of our thread. This guy will say, if I do not have a 1 list, split it in half, create 2 threads for each half, and then wait on those 2 halves. I have to wait on them before I can merge them because I need both the left and the right half to finish their job before I can merge them. Make sense? So that's my merge sort worker bee. So then out here, I'll go ahead and I'll say I'll create a merge sort worker bee. Let's see, we'll call this guy the first worker. And he will be equal to a new merge sort worker bee. And I'm going to pass him my array, the beginning of my array, and my array.length minus 1, the last legal bucket of my array. And then I'll tell that first worker to start. That actually starts the thread, calls the run method. Similarly, inside of merge sort worker bee, when I create 2 threads, I need to tell those threads to actually start. Left half dot start, right half dot start. That'll start those 2 worker bees, and then I will wait on those 2 worker bees. And the job of a worker bee is to say, if I'm not the 1 list, split myself in half, create 2 more worker bees. And this is what I was getting at the beginning of class when you were asking me, is you would actually have to make it a special case if you only wanted to do this at the top level. Otherwise, a merge sort naturally has built into it, let's have a worker bee do the left half, let's have another worker bee do the right half. The difference before was the second call to merge sort. So we're going to say this was our recursive call before. That second call to merge sort couldn't even start until the first call was done. Now, both halves are being worked on, quote, at the same time, with a multi-core processor very potentially at the same time. So they're all getting sorted up at the same time-ish, only to be finally merged together in the end. But we don't do the merge until both the left half and the right half have finished their job. Go ahead.
If you had a list that was like a million numbers long, would that like run out of threads and like die? Or does it do something different?
Okay, so the question is for everybody online is if we had a really, really, really big list, would we eventually run out of threads? The answer is, well, yes, eventually you would. You would run out of threads at a way later date than you'd run out of memory with a traditional recursion. Because we're not actually using recursion here, right? We're just creating new threads of execution. And we talked last time that threads are actually something considered lightweight. Okay, so a lightweight thread doesn't have all of the stuff that goes into a normal process, where a process has a lot of junk in it, which once you get into the operating system class, if you don't talk about it in normal operating systems, you'll definitely talk about the 450 class with me, where we're actually talking about effectively hacking operating systems. But you start thinking about what are the vulnerabilities and how the inner workings of the operating system actually work. Dr. Wall might also talk about this at some level in one or more of his security classes, maybe penetration testing. I'm not sure. Anybody in that class this semester? Have you talked about? Okay, yeah, so you're in the same, that these are the things that make computers vulnerable is the punchline. So this kind of goes back to Dr. Locklear's position on the grand ideas of computer science. I think I've joked around about it before, where him and I agree on very few things, and we've worked together for 17 years. So the fact that him and I both agree on that means it's probably pretty important, that all areas of computer science are all very related to each other. And you can't just look at one without looking at the other ones, because you're kind of peering into the same thing through different lenses. And that's why each of these classes, you start hearing repeated concepts, but looking at them through a little bit different angle or something like that. All right, so, but I guess to answer your question is, the answer is always going to be yes to a question like that, right? Because eventually you run out of memory. Eventually, I mean, the way threads work, and you might talk about this in the normal 350 class. You might talk about threads at kind of like the high level, and that is the way threads modernly work. You have something called operating systems that are something called thread safe. Is what they do is a single process actually creates a pool of threads that it hopes is enough to do all of its extracurricular stuff with, right? Not that you can't create more things in your pool, but the hope is that the pool is big enough, you're effectively pre-reserving memory so that your multi-threaded application runs faster. Now, with that in mind, is what we're doing here the best use of threads? Really, probably not. But what it's doing is it's giving us a proof of concept for probably what merge sort really lends itself to. So let's say that, so a thread allows us to pretend like we have multiple computers. I think that's a fair way of describing them. So even though we are using the same individual computer's resources, a lot of our computers today have multi-cores and all this stuff. So we got some resources to share. So any way you cut it, we're picking up some efficiency. But at some point, you're going to have diminishing returns, like you said, because you're going to spend so much time spawning off threads that do very little things. You're like, oh, is this really worth it? But what if we took that same gigantic data set that you mentioned, and we instead use Google's server farm, where we have thousands of computers that all take part in Google's search array or whatever. Where merge sort really shines in terms of performance is where you can actually offload the work to multiple machines. The idea being a distributed computer. And this is something that I definitely talk about in the 450 class, and Professor Locklear might talk about it in 350. But the ideal world for us as computer scientists, let's say, might be a distributed operating system, since our computers typically sit there idle most of the time. You know, if you're playing your video games or doing something else that's really doing a lot of heavy lifting, your computer is then very busy. But most of the time, our computers are doing nothing. Well, what if your computer was part of, you know, the global collective of computational power, right? And every single time you wanted to accomplish something, if you needed to do some heavy lifting, you could actually leverage not just what you had sitting in front of you, but a whole bunch of other people's collective power. So now you have, quote, virtually an unlimited amount of computing resources that you can share within a single application. Now things get a whole lot faster. That's something you probably talk about in, if not in penetration testing, you would talk about the normal security class, where we talk about, you know, how secure is your password, for example. You know, how many of you have ever been on a site that, you know, you get annoyed when they tell you about the number of things you have to put in for your password? Like the other day, we had to make a password that was a minimum of 18 characters long and had to use special symbols, which seemed ridiculous. But the reality is if you know if your password is made up of uppercase, lowercase, numbers, and symbols, let's say, so that is 52, 62, let's just call it 80 possible characters. Okay, that means that every single one of the characters in your password is one of those 80 characters. And if you have 13 characters, 80 to the 13th power is a big, big number, right? But it's not an infinite number. Now, if you have, so this is where what's called a brute force attack comes in, where you try to create every single permutation of those 13 characters made up of 80 choices. That's a lot for a single computer. A single computer maybe would take months and months and months or something like that for a number. I don't know how long it would take for this exact number, but extrapolate it out where if something was complex enough, a single computer would take lifetimes to do this. But if you distribute that work over 1 million computers, things get a little bit more suspect. Something that you thought was impossible to break before now it will be broken embarrassingly quickly. I may have told you this story in the 200 class, but there's a website called distributed.net that still exists today. Very old looking website. Hasn't been updated in a while, but it still does exist. And they have a client, and you've seen things like this where, you know, you can do like SETI at home, where you can download a client to help search for aliens, and they have folding, which allows you to do physics, like have your computer use its extra processes for physics problems, stuff like that. But distributed.net is you download their client and you're helping effectively crack encryption algorithms. And years ago, the government had come out with this algorithm called triple DES. And they said it was unbreakable. And you know, the challenge was you know, to try to break it. They wanted people to try to break it and prove it was unbreakable. Distributed.net broke it in 17 seconds, which, as you might imagine, is somewhat embarrassing for an algorithm that's supposed to be unbreakable. But distributed.net actually got second place. Another group of people actually created and this is actually similar to like Bitcoin mining. They created a special piece of hardware specifically designed for cracking triple DES. And I think it solved it in like 4 or 5 seconds, something like that. It really, really quickly. So these are called ASICs, application specific integrated circuits, where you just build a piece of hardware that's really, really good at doing one thing, something like that. And then you give it a whole bunch of cores that are all really, really, really good at doing that one thing. But in any case, just kind of an interesting problem. But this is the concept of where threads kind of play a role. So on one hand, what's the appropriate use for threads, like truly appropriate use of threads? You know, maybe when you have a software application and while you're, you know, maybe while you're using Microsoft Word, for example, and you're typing your paper or whatever, you kind of like the idea that maybe in the background every 5 minutes it goes ahead and saves a copy of your current work, something like that. But you don't want to really interface with that. You don't want to have a pop-up, you know, annoy you. You just kind of trust that there's somebody looking over your shoulder there that's just doing some side work, right? That's where you know, threads really shine, where you can have an application that spawns off 2, 3, 4 little worker bees that kind of handle some other things for you while you're working in the main thread doing your main task. So let's say that's where threads really shine. We're taking threads to kind of, as you pointed out, maybe a obscene level, but it's proof of concept for the level of what if I was able to distribute this across a whole bunch of computers? Now all of a sudden sorting becomes real fast. Does that make sense? So there's actually a technology called MPI, Message Passing Interface, that you can install on a whole bunch of computers. And what it does is it lets you effectively create a cluster of computers and lets you have those guys talk to each other. So now you write your programs like merge sort, for example, using the MPI libraries so that you can say, you know, wait for computer 1 and computer 2 to finish before computer 3 does the merge while I have 1,000 other computers doing their part. And now you're only limited by the number of computers you have, and each of those computers have multiple cores. So MPI can manage threads within each of those computers. So you still run into the same upper limit, right? If you have a big enough data set, eventually you run out of resources. So then you just say, oh, well, we can't solve this problem yet. Done. That's why data science is popular today, but wasn't necessarily that viable a decade ago or 20 years ago, because we didn't have enough memory. We didn't have enough processing speed to work with humongous sets of data. The spirit was willing, but the hardware wasn't really there to accomplish it. Make sense?
I have 2 more questions.
Sure, go ahead.
One of them is.
It's good that I answered them in such a quick.
So is a good example of like threading, like having music playing in like a video game, or is that something different?
Oh,
Like that's happening at the same time as everything else.
yes, but let me actually give you. So his question was, is an example of having threading like having music playing in a video game? The answer is yes, but let me actually give you a better example, very similar to that. In the early days of like iPhone didn't have multitasking, which is handled through threads typically. So if you had one of the early iPhones, if you wanted to be listening to Pandora, you could not check your email. Only the application that was on the screen was the one that was getting processing power. Right now, we take that for granted. You start your music, you bounce out, you're doing whatever else you want with your smartphone. But yeah, so I mean, I think that's a really good example of, oh, if we didn't have threads, what if? You couldn't use multiple applications at once. But certainly, if you're in a video game and music's going to play in the background, that would be a good use. That would be a good use of threads, I guess. Music, because you would probably notice. There might be other things that appear to be happening at the same time, but really they're all just happening really, really, really quickly, right? If you're going to clean the kitchen and clean the living room, and you do a little bit in the kitchen, a little bit in the living room, a little bit in the kitchen, a little bit in the living room, you're doing that fast enough, somebody from an outside observer might be convinced that it's all happening at once. Music, you'd probably hear the interruptions. So yeah, I think that's a good example. All right, so what's your other one?
Could you go into the driver and make this like a run?
Oh, you want me to run this?
Yes, please.
No, it just works.
It doesn't.
Well, let me finish looking at it first. Then we'll... All right, so what does our worker bee do as a run? So when we set up our worker bee, we pass it our array, we pass it our begin, we pass it our end. We set up those guys. Then somebody's going to tell our thread to start, which calls the run method with the extra magic of spawning off a thread. We're going to go ahead and print out that, oh, some stuff is happening, and we have a worker bee who's going to be working on our list between begin and end. As long as begin and end are not the same, meaning we don't have a one list that's not already trivially sorted, we'll get a begin one, an N1, and a begin to and an end to. We'll call our merge sort worker B on the left half, passing it begin 1, end 1. Merge sort on the right half, passing it begin 2 and end 2. Then we'll tell both of those guys to start, and we will then also join those two, which says wait for them to finish, because I can't merge the part of those that just began and end, that worked on the two halves. I can't merge them until they're both done, which means they also then have other worker bees that they're waiting on. All right, so then I go ahead and I get my two positions. Let's make sure merge is doing what it's supposed to do. I go through temp.length number of times. As long as pos1 is less than end1, or less than equal to end1, pos2 is less than, then we're going to ask, is the value at pos1 less than the value at pos2? If yes, store it, mark it as the winner. Else, store it, mark it as the winner. Otherwise, if pos1 is the one that's legal, store pos1, mark it as the winner. Otherwise, pos2 must be the legal one. So store pos2, mark it as the winner. Then we'll copy it back over. So temp pos goes from 0 to temp.length minus 1. AR pos goes from begin to end, including end. Keep going as long as temp pos is less than temp.length. Increment temp pos and AR pos each time through. We'll set AR at AR pos, overwriting AR, equal to whatever temp currently has in it. Okay, so it looks reasonable enough to me. So here we already filled up our array. We printed it, proving that it worked. We created our first worker bee to start the job here. We told that worker bee to go ahead and start. Now, before we can print out our result, we're going to need to say first worker dot join. And then we can say driver dot print array AR. And we need to do a try and catch on this, because we can't print out our resulting sorted array until it has finished doing its sorting thing. So we tell it to start sorting, then I'll wait for him to be completely done, which means all of his worker bee threads have finished and I've done all my merging and stuff, and then I should be able to print out the final result. That looks right. Didn't that work?
I think so. Mine didn't.
Oh.
I don't know what the hell I was drawing.
Okay, but we see here as we go through how many we have. You know, these are all threads that were started, everything with little asterisks next to it. You know, so this guy was working on 0 to 19, then 0 to 9, and 10 to 19, 0 to 4. And notice here, you actually see the mixture. 0 to 4 and 10 to 14 were happening at roughly the same time. Even though these guys aren't right next to each other, we were working on different portions of the array at the same time. And this is just how they were scheduled. And we had 15 to 19. Here's the 5 to 9. Okay, just like we saw last time, these guys were kind of being, they were kind of happening interchangeably. We don't have control over when that thread gets CPU time. That makes sense? We don't get control over when that guy gets CPU time. All that, and that's why we need to have those joints. We can't play the game of, let's just see if we can balance the speed. I use the double dragon example of, you know, all the bosses come out at once. You know, we have to say, look, we have the benefit of having multiple things happening at once, which is awesome. But we need to also say, okay, I cannot continue until I hear back from all my workers, right? I can't go to the farmer's market and sell my vegetables until all the people have picked them for me and delivered them by truck. I don't know why I use that as an example, but it's an accurate example. I hate farmers markets because you have to cook that stuff. I'd rather go to places that already have everything prepared. I could just start the feeding. Well, that's why you have a weight problem. And probably a busted knee. All right, So questions on the multi-threaded merge sort stuff? Let's see, chat. They are automatically killed. Automatic garbage collection. And so Zach is asking, are the threads automatically killed when they are completed, or do they stay in memory? When they finish, we have this thing called automatic garbage collection, and automatic garbage collection will kill off unused memory. Now, having said that, that is a convenience for us as a modern programmer, but it actually also then does take some system resources, and also is an example of a thread. So we have this thread that is running inside the Java virtual machine. We could think of it as kind of like a garbage truck, right? And he just runs up and down memory looking for things that aren't currently used. They have something called a pointer count associated with them. And if you find something that's pointer count is 0, that means nothing's using that dude. It frees it up and tells the operating system, you can hand out this memory again to somebody else. Go ahead.
What kills the thread that kills the thread?
What kills the thread that kills the thread? Well, it would be the Java virtual machine that manages the threads within a single application running. So when the Java virtual machine exits, since threads are children of that process, threads are managed by their parent process. They're not managed by the operating system directly. So when the Java virtual machine ends, your program ends, all of the threads that it created die with it. Whereas historically, that if you used the fork system call and you created multiple processes, just because the parent process died, you still got millions of other ones floating around out there. It's a problem, right? Then it's up to the operating system to say, okay, what do? I need to go start killing off processes that share the same name as this dude that was running amok, something like that. But that's also why things are safer as threads, is we only need to kill off the top level process that spawned all those threads in order to have all of the threads die. But then if your top level process doesn't die, he's an infinite loop or something like that, just keep spawning off threads, that's where you have to have some sort of management, or external intervention. A system administrator needs to come in and kill off that rogue process that, is trying to take over your PC, whatever.
So can I break my laptop by making a program that says while true, create a thread?
You could make a pretty good attempt at it. I would say if you were asking that question 15 years ago, the answer is yes. Today, because that's a very common way of attacking operating systems, your operating system probably has a thread limit, which is kind of related to your question you asked earlier for an individual process, where if you wanted to use more threads than that, you have to specifically give it command line arguments for that to accomplish it. So I would say probably not today if you're running a modern operating system, but you're definitely throwing punches at it, and it's just equipped to deal with them. Yeah, I mean, you roll back, and I'll answer James' question here in a second, but if you roll back a bunch of years, when your first programming language might have been C. This is way before we had operating systems that created kind of a little virtual space for every running application. And we've talked about pointers and stuff like that in here, and we talked about kind of how Java protects us from ourselves. A beginning programmer, we can walk off the end of an array. A lot of times, if you're in the security class, they might call those buffer overloads or buffer overruns, something like that, where a buffer is like an array, and if an array has 100 buckets and you start screwing around with memory address 101, 102, 103, you're off the end of that array and you're into some other part of the computer, somebody else's memory. Well, Java protects us from that, gives us a nice array index out of bounds exception. But if we were in an older language like C, in an older operating system like Windows 3.1 or DOS, you potentially could be working on your C programming homework for your computer science class and actually have to restart your computer because your program had a bug in it. and you took up all your system memory, or you overwrote half the operating system in memory or something like that. You would have had to, that's part of the homework experience is, oh, I had to, I crashed my computer running my program over and over again. And even before that, you would have had punch cards where your whole program was, on these pieces of paper where you punched out these cards. You had to take them to a stack and have them batch processed. If the cards were bent a little bit, it's kind of like putting a dollar bill into a soda machine. It didn't quite fit. We should really appreciate what we have today. Life has gotten a lot easier, which makes it that much more impressive when you see there's a good book called what's the name of it? Let's see. Outliers. The name of the book is called Outliers. And it talks about, kind of what things lead to success. And I feel like I mentioned it in class last semester. Okay. But one of the things it specifically talks about is, kind of the idea that the things that might make us good at something are sometimes opportunities that other people might not have. And, we all can recognize that at some point, right? If we're somebody who's working 3 jobs to put ourselves through school, you kind of feel disadvantaged over, somebody else who has, wealthy parents who are paying their full bill and they don't have to work and stuff. But I mean, this is reality, right? We accept this as reality, and it's not that other kid's fault that he came from a wealthy family. It's not your fault that you're having to make it on your own, but it still has consequences, right? And one of the things that book talks about is the whole Bill Gates situation. Why our richest people in the world right now, and really the richest people who've ever lived, all grew up in a very tight period of time. It was kind of in that time where computers were first kind of becoming a major thing. Obviously, computers have taken over the world, right? We rely on them almost infinitely at this point for our world to work. But you have this group of people that grew up at the right time. So take Bill Gates, and Bill Gates went to, and this is before you had personal computers. He went to a school that had some fairly wealthy donors, as well as somebody who was working on one of the original supercomputers, who donated it to the school and wanted their brightest people to just go around and play with it, to mess with it. So Bill Gates and his couple of buddies, they came in and they started playing with this computer technology nobody else had access to. They had this advantage. So it's really a kind of a fascinating, fascinating type thing. And when you read the book, there's just so many things in there that, you're like, oh, that completely sounds true, and I would have never considered that. Like one quick example was, they took 10 American, I think 15-year-olds and 10 Chinese 15-year-olds and gave them each 7 numbers and said, you have to memorize these 7 numbers, you have 30 seconds. 100% of the Chinese 15-year-olds could memorize all 7 numbers. Less than 20% of the American 15-year-olds could remember the 7 numbers. Why? Our natural go-to mentality might be that, oh, well, maybe those Chinese students were just better at math. That's kind of our stereotype thing, right? It ultimately came down to the efficiency of the Chinese language versus the English language. The human brain is on about a 2-second loop. This is related to kind of our threads we're talking about. So whatever we can accomplish in 2 seconds, we can conveniently store in our memory. The English language isn't efficient enough to say 7 numbers within those 2 seconds.
Were these like really long numbers or like?
Not necessarily. Yeah, the Chinese language was. It was efficient enough to fit all 7 numbers within that 2-second loop. So it had nothing to do with them being smarter, better at math. Parents beat them until they finished their studies. None of that stereotypical, the Chinese are better at math. None of that stereotypical stuff. It all had to do with the language, right? So fascinating things like that. Really, really interesting book. The same author also wrote another book called Blink. that's equally interesting. So Malcolm Gladwell is the author. Highly recommend that. Let's see. When a computer shuts down, wouldn't that kill all threads within a computer? And would that be the thread that kills all threads? That's true. When a computer shuts down, anything that was living in memory, any application that was running in memory is killed. Because the way our memory works in our computers is it must maintain electricity in order to keep whatever's in there. So yeah, the best way to, a computer that's currently being overwhelmed with multiple processes or multiple threads, the way to fix that is to just restart the computer and don't run whatever program started that again, is the punchline. Which is why a hacker might try to insert that destructive program into the startup sequence, right? That's why like Windows has a safe mode where you can boot it up in safe mode, where it only starts the most important official processes to get the ball rolling. That kind of thing. Yeah, so now we're kind of getting into an operating system type of situation, but in any case, I think that is a reasonable. Well, in any case, these are all related things that are important, but not necessarily important for us in here. For us in here, we really want to look at threads through the lens of, hey, what if I want more than one thing to happen at the same time? But hey, what if I need to wait for some of those things to finish before I can move on? We can do that. All right. I think I mentioned it last time. A really good use of threads that we can all relate to is when we log into our email or something like that, or you do a Google search. Let's say you do a Google search. How many Google searches happen every second? Rounding down a lot. We're actually rounding down a whole lot, probably. Okay, what if only one person could do a Google search at once and it was just first come, first serve? That would suck, right? What happens now? We all go to the Google webpage. When I get to the page and I type in my search thing and I press enter, a worker bee is created for me, and that person is interfacing with me, allowing that page to now handle another query and another query and another query. And then we get to what we talked about earlier, where Google then has a farm of actual computers, each having lots of hardware, lots of resources that are handling all of those simultaneous tasks. Not that it's infinite, not that it can handle an infinite number of requests at once, but it can handle rounding down a whole lot at once. All right, so questions about any of that? Okay, so for next class, we're going to go to developer.android.com. We're going to spend the last part of this class writing some Android applications, which is going to be taking our Java knowledge, and you're going to see Android is kind of built on top of Eclipse, so there's going to be a lot in common, but we're going to be taking our Java knowledge and applying it to a graphical user interface through Android. Now, we're not going to make really complex things. We're just going to see our Java knowledge working within that framework, okay? So we're going to go to developer.android.com, and we want to get Android Studio installed. So if you scroll down here, we have this thing called Android Studio. You can go to download.
So are all Android applications written in Java?
All native Android applications are written in Java. Yep. So you're going to download Android Studio, and then I'm going to put a link to a Hello World tutorial. Get your first Hello World application running on Android, and that's what we do on Tuesday. If you have a computer with an AMD processor in it, or if you get an error that says something along the lines of unable to initialize virtual machine or something like that, you might have to go into reboot your computer and press like delete or F8 or something like that to get into the BIOS and turn on virtualization. If you do a Google search for it, most of you will not have to do this. Most of you it'll just go fine. But if you do have a problem with this, do a Google search on it. You have to look up, how do I get into my BIOS on my computer? It only takes like 2 minutes to fix, but just be prepared if you're one of those people that gets the virtualizer issue and you can't run the virtual machine, because what's going to ultimately happen is your computer is going to launch a pretend Android device on your computer, an Android emulator. Okay, so I'll put up the links that you need to go through. So install Android Studio, get it all up to date, and get a Hello World program working for Tuesday. On Tuesday, I'll start going into how do we accomplish some very simple stuff in Android Studio. You're not going to be writing amazing applications, but we'll start getting our user input through a text box and that kind of stuff. Sound good? Questions, comments, concerns, bribes? Okay. I will see actually, hold on. We're not out to 12:50, are we? Oh, I thought we were 12:35. Good.
I thought you were just ending early.
No, we're not. We're not. I appreciate it. Which is my class ends at 35. Oh, it's my next class. My next class ends at, this one ends at 50. All right, so with that in mind then, let me go ahead. I'll grab because mine's pretty old. So I'll go ahead and grab the latest Android Studio. While it's downloading, I'll start talking about some Android stuff. So if you do have Android Studio on your computer for some reason, you've dabbled with it before, grab the latest one. That way we're all at least using the same starting point. All right, I'll go ahead and put this into applications. Notice it's trying to overwrite my old one. I'll say replace. I'm on a Mac, so if you're on a PC, it'll do something similar but different. So I'll go ahead and say replace my old Android Studio with this new Android Studio. I'm kind of excited because I haven't actually used Android Studio in probably over a year. So I wonder how much it's changed. All right, so now I have Android Studio installed on my computer. I'll go ahead and open this guy. The first time that you run it, you're going to probably have to do some system update stuff. All right, import Android Studio settings from my previous version. You probably won't have this, but if you do, feel free to go ahead and do it unless your old one was just completely busted. So I'll import that. Let's see, directories below contain configuration system files for unused version of Android Studio. Check the boxes needs to each directory you want to safely delete. Fine. Now, in the early days of Android, before they had the product called Android Studio, the way you did Android development was actually to download Eclipse and then get the Android plugin for Eclipse. That's why you'll see quite a bit of similarities between Android Studio and Eclipse. One frustrating thing with Android Studio, once you kind of get used to working with it, it's not the end of the world, but you'll find out that it's very heavily, it's very actively being developed. So it means you'll get updates and fixes and things like that relatively often. Usually this isn't a problem, but you almost feel like the application is bugging you. It's like constantly reminding you of something new. Okay, so there's a couple of updates here. So any updates that pop up initially, go ahead and do. So I'm gonna update all the stuff here. We do have this thing called Gradle. Gradle is the tool that and I'll introduce some of these things, but it's the thing that actually builds your application into an Android, what's called an APK. Relatively unimportant for us. So I'll go ahead and update that guy. I'll also go ahead and update this other Android Studio thing. So I'll say update now. So anything that's screaming at you about updating, update is the punchline. This will get your Android Studio installed and fully up to date and all that stuff. And I'll actually go through assuming this goes through quick enough, I'll go through the Hello World thing. But let me start while this is doing that stuff. I'm going to create a new slide. All right, so we have this concept called design patterns. All right, so design patterns are a proposed good solution to a common problem. We talked about design patterns before? Last semester or anything? Okay. So the concept, this is a broad concept called design patterns. This is a proposed good solution to a common problem. Now, these guys commonly have crazy names, and they are somewhat abused. And what I mean by that is, how many of you have ever heard, this is among academics, have you heard the phrase publish or perish before? So with academics, you know, if you're in a research institution or something like that, basically one of your job requirements is to write research papers and, you know, move forward the field that you're in, something like that. Hence, you need to publish research, publish papers. So design patterns have been abused from the perspective of this publish or perish type idea, where let's use a real life example, making a peanut butter and jelly. Okay, most of us, if we had to, could make a peanut butter and jelly sandwich, right? But some of us might have that special trick. Like, oh, well, you put the peanut butter on first, then you put the jelly on, and you got to only do it on one half, or, you know, you kind of get where I'm saying. You have your own little approach to how you handle it, something like that. Well, you might say that your solution to making a peanut butter and jelly is a good solution. In fact, you might argue it's the best solution. Somebody else might have what they argue is the best solution. Both of those could be design patterns for making peanut butter and jellies. And you just come up with a crazy name for it, and that makes it qualify as a design pattern. That's kind of a joke, but it's also a truth. But in any case, this idea of a design pattern, we can almost apply to anything. And your idea of how you make a peanut butter and jelly doesn't have to be that great, right? I mean, Mr. Gonzalez stands on the other side of the room, just throws peanut butter and throws jelly at pieces of bread that are laid on the counter. You can imagine how successful it is, but that's his proposal for making a peanut butter and jelly. All right, and he could publish that and get it in a journal and all that stuff. So one issue we have with design patterns, the generic concept of design patterns, is there's a lot of them out there, but only some of them have kind of bubbled to the top as being adopted. Okay. Let's see where we are over here. Finish that guy. Okay. I'm going to pretend like I don't care what's new. Okay, so this is an old project. So I'm going to say File, New Project. And what I like to do is so it gives you this template for starting points for activities. So let me give you a little background for this. Let me finish this little design pattern thing, since I can give you a tutorial for the Hello World thing. So we have a design pattern called MVC. That is Model View Controller. Model is the data we store. View is the visual user interface. Controller is the behind the scenes logic. For us, this is Java. Okay. Model View Controller says it's a good idea to keep your model, view, and controller separate, and then have some mechanism for allowing them to communicate. It's important to note that, I'll actually put this on the previous slide. A design pattern is not an implementation. It is a suggested approach that can be used in an implementation. Okay. with that being said, MVC, this concept is saying, hey, and really the problem can be, if any of you have ever written any websites or anything like that using PHP, I don't necessarily expect that you have, but if any of you have, as websites become more and more complex, PHP is a single document that has your user interface, that's your HTML code in it, plus your logic, your PHP code in it, and then it might also have some stuff that talks to your database and stuff, all in one file. And if your page gets complex enough, you look at that and it's just spaghetti code. You got a whole bunch of stuff where you got user interface stuff and logic stuff and database stuff all stored inside of a single file. And it's very hard to manage. So it says, hey, you know, it's a good idea. Why don't we put our logic stuff in one file? Put our interface stuff or HTML stuff in another file. Put our database stuff in another file. And then link those files together somehow so that we can manage our application in a reasonable way. If I need to update the view, the image, the user interface, I'll go to one place. If I want to change the way it works, I'll go to another place, so on and so forth. Okay, so MVC says that's a good idea. Now, Android has their own approach to MVC. iPhone has their own approach to MVC. When you're in the 370 class next semester, the software engineering class, you're going to be using Visual Studio.net. They have their own approach to MVC. So this concept, this design pattern exists in all of these different applications for making, you know, MVC would be something for making user applications. But they're not all implemented identically. So you kind of have to learn the Android's version of MVC. How do I programmatically get access to a button that's on my interface? And similarly, how do I get a text field in my interface to update based on my logic? Put some text in there or a label in there, something like that. Okay, how do I make all these pieces talk to each other? That's what MVC effectively is saying. All right, that makes some sense. Now, when we talk about Android, an Android application is a collection of something called activities, where an activity is a collection of views. I'm going to just call it controllers. So the interface, the code that runs the interface. We're going to leave the concept of model out for right now, since we're not doing data storage right now. We're really thinking about, I have my pretty user interface, I have my code that drives those. How do I make those dudes talk? That makes sense? All right, so just to get you started here, I will almost always start my starting activity as an empty activity. Any of these other ones, basic activities, bottom navigation activities, they already have a bunch of stuff done for you, which is fine. If you know what you're doing, you've been doing this for a while, you're making a very specific application, whatever, that's all fine and dandy. But my feeling is the cleanest starting point for an Android application is having an actual activity that doesn't have anything pre-done for you. Go ahead.
Is that kind of like how you wanted us to type in like public static void main on our own instead of like having it pre-generate that? You want us to like
it's probably related. It's probably related to doing that. But so you'll see what happens here just real quick. I know we're basically out of time, but let me just say, if I say empty activity, I hit next. It's asking me, what do I want to call my application? I'll just say my application for right now, and I'll let it store it wherever it's going to store it. The language is Java rather than Kotlin. Kotlin's like their competitor to Swift. It hasn't taken off. So Java is what, this gets back to your question about what are all of them written in. Minimum SDK, notice it's pre-chosen API 16 Jelly Bean. That's a pretty old version of Android. And the rationale for that is if you have an Android device, chances are it's at least that new. I mean, if I go up to the latest, greatest Android Pie or Q, very small percentage of people are actually running that. Okay, notice here it says your app will run on approximately 99.8% of devices with Jelly Bean. If I choose Q, now it's down to 8.2% of the devices. So your app is likely not going to be as available, whatever. Okay, so I'll go ahead and hit finish here. And what it'll do is it's going to create my Java activity for me here, but it's also going to create my user interface. MVC. Here's my controller. And then here's it's loading it right now, but which isn't important, but this is my user interface for it, my view for it. Okay. So what I'll put up is a tutorial for getting a Hello World application going in Android Studio. So your goal for Tuesday is to have a running Hello World application in Android and submit a screenshot of it. Sound good? Questions, comments, concerns, bribes? All right. I'll see everybody on Tuesday.
Is this stuff like capable of going on GitHub?
Oh, yeah, absolutely. Yeah, absolutely.
We're not
Yeah.
doing that though.
We will. I'll show it next time. But yeah, for the Hello World, just give me a screenshot. Yeah. I basically just want you to have your development environment set up. It's the punchline here.
Oh, so I downloaded it while you were talking. What is it loading?
This.
Oh, okay, cool.
Yeah. And notice it already has Hello World in it. So if I go and hit play, it probably already has one of my virtual machines. They're called AVPs. So it's launching my virtual machine here. And it's probably just going to pop up Hello World when it's done launching. The first time through, when you do it, you'll have to create your own virtual machine. But notice it's launching Android here as if it's a real device. And when it's done, it'll just have Hello World on the screen.
And will it like launch this like every time you use it?
No, well, yes, but if you're working, once it's launched once, it'll stay launched. Then when you run it, it'll run almost instantly.
Yeah, it took way longer than I thought it was going to. I thought I was going to have to sit here for a while.
And there's Hello World.
Hey.
So I just did your homework. That's what your homework should look like. And I'm still recording here at the end of the video. So, but this proves that you have it all working. This part right here, I'll just leave it on the video. This is the piece that you might get that virtualization issue.
Okay.
Very small percentage of the people, but it's a headache. So that's
you just go into the BIOS for that?
Yeah, do a Google search. It'll tell you exactly what to do, but it's one setting in the BIOS, and it's mostly seen with AMD processors. But you're not guaranteed it to happen with an AMD processor, and I think I have seen it with an Intel processor before.
So why did that happen?
It's because of how the virtual machine actually works. It's trying to bypass your operating system and actually use your direct hardware. And your direct hardware, it's used for performance reasons. The old version of Android Studio, when you first launched it, you saw this launch pretty quickly, relatively speaking. It would take like an hour for the virtual machine to launch. So at that point, you don't want to close it down. You leave it open through, you close the you lid your laptop. Otherwise, it was just slow as heck. So it's improved a lot. Yeah.
Could you call someone on that?
You actually can. Yeah, it has. You can do fake GPS stuff, and yeah, a lot of people were using this to like hack the original Pokemon Go.
Oh.
To change their locations, they go collect stuff because you can fake GPS location on it. You can also do that on your own phone now too with Android. See, more you know.